Hi everyone, welcome to Vedantu NEET English. I'm Diksha Ma'am, your chemistry master teacher. So everybody do let me know in the chat box if I'm clearly visible and audible to you so that we can start with our session where we are going to discuss about the EM waves, right? Wait a minute, where it is? Yes, here it is. We are going to discuss about EM waves, that is electromagnetic waves, the properties of electromagnetic waves. Then we are going to discuss about black body radiations, photoelectric effect, and Planck's theory, right? Okay, everybody. So very good evening, very good evening, Asinath, Maz. So guys, firstly, tell me in the chat box, is there any problem in the previous lecture of discovery of electrons, protons, neutrons, right? We discussed about all of that. So if there is any problem in that, you can let me know in the chat box and we shall start with our lecture, right? Okay, guys. So let us discuss what are the EM waves, that is electromagnetic radiation, right? So as the name says, it has electric field and magnetic field within itself, right? So if I am saying this thing, so in this thing, if I am saying wave is propagating in this direction, this is where the wave is propagating, then the electric field will be perpendicular to the propagation of wave, and magnetic field also will be perpendicular to the propagation of the wave. Perpendicular means at a 90 degrees angle, right? And these electric and magnetic field are going to be perpendicular to each other. That is called the electromagnetic wave. That means it has propagation of wave that is in one direction, electric field, and you have magnetic field, and all of these three things are perpendicular to each other. That is called as electromagnetic radiations, right? Now let us talk about some characteristics of electromagnetic radiation, some terms that you must know before understanding electromagnetic radiations, right? So let's understand about these terms. First is, what is this crest, what is this trough, right? So guys, the upper peak, that is called, that is above, that is in the positive direction of the wave, that is called as crest, right? This is called as crest, and the one that is in the negative side is called as trough, right? So total, if you see here, I can see three crests, 1, 2, 3, and 3 troughs are there in this particular wave that you can see on this board, right? Now, let's understand other terms like amplitude. So, amplitude is the maximum height of that wave from the origin till the peak point, right? So, from this origin till the peak point, what is the height? That is called as the amplitude, right? Or you can say even here, that is called as the amplitude, right? So that is called as the amplitude of the wave, and amplitude will define the intensity of the wave, right? More is the amplitude, more will be the intensity of that wave, right? Now let's talk about the third thing, that is, wait a minute, let me just show you that, that is wavelength, right? So wavelength is also called as lambda, right? What it is written as? Lambda, lambda, right? Now, wavelength, as the name says, right, it is like a length, right? Like we follow distances, right? When you're traveling somewhere, you will calculate your distance. What is the distance? 1 kilometer, 2 kilometer. In the same way, we have here wavelength. What is the length of that wave? And what is one wave? We are discussing wavelength is the length of one wave, right? Just one wave. And what is one wave? One wave is, you can write it here, one wave is crest plus trough. Crest plus trough, right? That together will make one wave. If you see this here, starting from here, then here, then here, this particular thing is going to make one wave. Okay, so even if you see directly, you can say that distance between two crest, distance between two trough, right? So if you see this here, if you start from this thing, if you start from the origin point, right? If you start from 0 axis, right? That means 0 point of the x-axis, then you're going to say one crest and one trough, that makes one wave, right? But what if they start from this side? Then one crest and other crest. What is the distance between two crests, two consecutive crests? And what is the distance between two consecutive troughs? For example, what if I start from here? Then this is the next trough. So what is the distance between two consecutive troughs? That is called as wavelength. Why I'm telling you all these things? Because sometimes in the exam, they don't directly give you lambda. They give you that this distance is called as, let's say, x. Now what will be lambda? Lambda will be x only, right? So for that, you should also know what it actually means apart from the formulas also, right? So wavelength you can say distance between two crest and two trough. If you see the distance between two consecutive crests and two consecutive troughs, that is called as one wave, right? Now, there are some other important characteristics also that I'll just tell you here, right? Next thing is, if you talk about frequency, right? So what is the frequency? So let's say frequency, like in general life, what you call frequency. Ma'am, what is the frequency of your lectures? That ma'am, how many lectures you take in 1 week, right? My frequency is 4, right? So if I ask you, how much is your frequency of practicing the questions? Ma'am, maybe I practice every single day I practice the question, so it is every day. Okay, how much is your frequency of giving mock test, right? You say, ma'am, yes, my frequency is like after every 15 days I give the mock test, right? So that defines your frequency. Similarly, if I talk about these two things here, right? This is one wave. If in the parallel thing, if I draw this kind of wave, right? And here parallelly, if I am drawing this kind of wave, can you tell me which one has high frequency? In 1 second, which will be more? This in 1 second, if I say 1 second, I am stating by this thing, okay? Between this point to this point, there is 1 second, okay? So here you have just more than one wave it is there. And here you have 1 complete, 2 complete, or almost 3 complete waves you have here, right? Almost 2 complete, 2 point something, almost 3 complete waves you have. That means in a certain fixed interval of time, right? If the frequency of wave is more, that means that is called as frequency is more, right? That means number of waves per unit time is called as the frequency. So what you can say, frequency is nothing but it is number of waves per unit time. Per unit time, what is the number of waves? That will define the frequency, which is called as mu. It is not V, it is mu. Okay, little bit curve is there. Okay, that is mu. Now, this mu has units of per second because it is mu is equals to 1 by t. So it's unit hour per second, or it is also called as hertz. Why units are important? Because when you're doing the questions, you have to understand this from the units, right? That what they have actually given, right? Okay. So that was all about wavelength. We have done frequency, we have done, and what is the speed here? So speed will be exactly same as speed of light. So we will say speed will be equals to 3 into 10 raised to power 8 meter per second always in these cases, right? Now guys, there is one more term that is regarded as wave number, right? What is that term? Wave number. That also you will see throughout this chapter. Wave number, right? So what is this wave number? What is this wave number, right? Wave number is represented as V and a bar on it, right? A line on it. This is called a bar, okay? V bar. See, mu is this thing, right? V bar is wave number and lambda is wavelength. So these are the three different things that you will see here, right? Okay. So now understand one thing, guys. Understand one thing, that if I talk about wave number, it is right? It is very simple. It is wave number is just inverse of lambda. That's it. Wave number is 1 by lambda. That's it. What you have to remember, right? It is the inverse of the wavelength that is called as wave number, right? So these are the three important things that we are going to discuss throughout this chapter: wave number, lambda, and frequency, right? Okay. Now, let's understand the electromagnetic radiation. See, most of the radiations around us is electromagnetic, and this is very interesting, very interesting. Okay, tell me one thing. Is there some, if you touch your hand, right? If you touch especially your hand, you will see your hand is warm. Can you feel that, right? Your hand will be warm, and when you sit outside this, like when you sit in the sun, what you will see, that there will be some heat that is coming out of your body, which you can't see exactly, right? With the, like with naked eye, you won't be able to see that. So basically, the rays that are coming out of our body every single time, not only us, every single thing around us is emitting some kind of radiation, right? Some radiations you are able to see. For example, this light that is focusing on me, right? This light that is coming on my face, you are able to see that, okay, this tube light, I'm able to see that it is coming out, right? Why? Because this is lying in the visible region, right? It doesn't mean that this light is not emitting more radiation. It is emitting. It is emitting some radiations in IR region, some radiations in UV region, right? Like you have UV rays from the sun. Can you see those UV rays? No. Can you see that, okay, I'll apply sunscreen because I can see UV rays coming here? No, you can't see that because they don't lie in the visible region. So all the things that our eyes can see lies in this visible regions. That's why I have made it as a colorful thing. Everything else is just what we can't see, right? So this is all together a electromagnetic radiation. In that electromagnetic radiation, we are only able to see the visible lights, right? That is VIB-GYOR. What is that? Violet, VIB, violet, indigo, blue, G, green, GYUR, yellow, orange, and red. This VIB-GYOR is only thing that we are able to see, right? Our body is emitting IR radiation, we are not able to see that, right? Okay. So now, what they ask you in the exam regarding this, simple question is asked based on this. That is simple question on the spectra, right? If you learn this, you are sorted. Like a simple question based on this spectra is asked, right? And how they ask you this thing? Arrange this spectra in increasing order of wavelength, in increasing order of frequency, in decreasing order of wavelength. These things are asked, okay? So for these things, you need to understand one thing, that I'll just define it here. You need to understand one thing, that always C is equals to mu lambda. Now students, C was speed of light, mu was frequency, multiplied by lambda, that is the wavelength, right? Now, if you see this, speed of light is constant that I told you, right? This is 3 into 10 raised to power 8. So can I say that frequency and lambda are always inversely proportional to each other? So can I say that if I am saying that this wavelength increases in the order, that means this is the increasing order of wavelength, right? What is written here is increasing order of wavelength. That means this has maximum lambda, this has minimum lambda. This has minimum lambda. So frequency is going to be opposite. This will have minimum frequency and this will have maximum frequency. And you should remember only one thing, that increasing order of lambda is gamma x UV. There is a gamma, there is a guy named Gamma, right? Or a girl named Gamma. Or you can say girl x UV. There is some girl whose X name is UV, Yuvraj Singh, right? So gamma's X is UV, right? Gamma's X UV. Visible information. Everyone is able to see what he is doing, right? Visible information, micro radio do it, right? So gamma x UV, visible information, infrared, right? Micro radio, MR, right? Visible information, MR, right? Visible information, MR, right? So you can remember this whatever way that you like, right? It's not like you have to remember this like what ma'am told only. No, you like just relate it with your life, right? Because these kind of orders, you can't remember it by heart like that. That okay, this is gamma, this is UV, this is X, this is radio, this is micro. Very difficult, right? So try to learn it with the help of mnemonics, right? Okay, make your own mnemonic. Now, if you see this here we have this VIBGYOR. Now, any one of you, I am telling that this is increasing lambda. So that means red will have maximum lambda. Can I say maximum lambda, minimum frequency out of VIBGYOR in the visible range to our eyes, right? Lambda maximum is of red color, right? Okay, that's why it is so bright, right? It is so bright. It is visible to us like anywhere because its lambda is very high. And if you talk about violet, its lambda is very less, right? And its frequency is going to be maximum, right? Okay, is that clear to everybody regarding electromagnetic radiation, the order, right? And how it is fluctuating with gamma and frequency. This is all what you have to learn from here, right? Okay, let's talk about some of the important points of electromagnetic radiations. So first is a source emits continuously in the form of radiation, no change in wavelength or frequency of the emitted radiation even on increasing the energy radiated. So basically here I think this is not a point of electromagnetic radiations. I'll just correct it, right? My bad. This will be black body radiation. So now guys, we have our second topic, that is black body radiation. Now tell me how many of you are ready for it? How many of you are ready for black body radiation? Because it's a very interesting topic, right? I'll just erase it here because I know there might be some confusion because of that, right? Okay, so now let's talk about black body radiation, right? Two effects, guys, we are going to study in the electromagnetic radiations, right? That is going to be, see, I'll tell you why this is happening, okay? Why this is happening, let's discuss that. Why this is happening? First answer question is why, okay? Why wave nature is not enough. Now, if you understand physics, right? In physics, we all are talking about dispersion, diffraction, refraction, reflection, interference, right? All these phenomena, your Young modulus experiment, all these things are based on the wave nature of electromagnetic radiation, right? It is more detailed in your physics, right? So we are sure that, okay, electromagnetic wave is a good thing. It is a wave. We are sure on that. But now, these are the two phenomena, right, which starts questioning the wave nature of the electromagnetic radiation. Because by black body radiation also it is symbolizing that it is a particle nature. And photoelectric effect is also symbolizing that it is a particle nature. And that is our today's topic, to understand how from wave nature we are moving towards particle nature, then dual nature. What was the need of it? Who saw this dream that no, this is not a wave nature, this is a particle nature? So there must be some phenomena behind it, right? So that phenomena is black body radiation and photoelectric effect. Okay. So guys, I know that very few of you have actually understood black body radiation, right? So don't worry, it's actually easy. And I feel that, I don't know, I feel in NEET 2026, very high probability, not a difficult question I'm saying, a very simple graphical question based on black body radiation will be asked to you, because it's not difficult, it's a ignored topic, right? And you know that NEET is right now focusing on the ignored topics. Okay, students are not focusing on this, let's put this question in the exam, right? And they will not give you a difficult one, they will give you a very simple question based on black body radiation, right? So let's understand it. Okay, let's understand it with the help of a simulation, right? So I'll just show you one simulation over here, right? Let me just see that, right? So here we can add black body radiation, right? Black body radiation. Okay, I think so it should be there. Yes, here it is. Black body radiations. Okay, so firstly I'll tell you see, it's very, very important to understand this, but for this you please have little patience, right? Try to understand what I'm saying. Okay, so in black body radiations, we are talking about that. Firstly, you need to understand what is a black body, right? So to understand what is a black body, let's understand this with the help of this diagram here, right? What is a black body? Yes. Okay. So let's understand what is a black body. So a black body, we know that there is any body, right? Any kind of an object. It will absorb some radiations. Okay, some radiations will fall on it. Some radiations it will absorb. Some radiation it will emit. Right? That is a simple body, right? But if we talk about a black body will absorb, what it will do? Some radiations will fall on it, right? Now inside what will happen? Let's say this is that object, this is that object. Some radiations are falling on it. Radiations are falling on it, right? Now when radiations are falling on it, what will happen? Inside the body there will be atoms, right? These atoms, electrons, they will gain that energy. So in a black body, it will not emit, it will not transmit the radiation. It will absorb 100% radiation. It will absorb 100% radiation. That is called as a black body. Now, ma'am, what this black body is going to do with this 100% radiation, right? This radiation will fall on it. Every single radiation, like from sun, anywhere these radiations are coming, we know that these radiations carry some energy. So this particular body will have radiations, have energy of these radiations. This body will have energy of itself also, because there are some particles inside it. These particles, because of these radiations, will gain some kinetic energy and they will also start moving, right? They will also start moving, right? And you know, the simplest example in your daily life is black clothes, right? So why we talk about black clothes, right? Don't wear black clothes in the summer. What is the reason? Because it will get warm very easily, right? Why? Because it absorbs the radiations from the sun, right? It does not emit the radiations from the sun. Yes, our black clothes are not 100% black body, right? There is very rare, I would say 0%, 100% black bodies. But we talk about in general, we have gray bodies, which are not absorbing to 100%, but almost 100% they are absorbing, right? Okay. So if you talk about this, why don't we wear black clothes? Because it is not going to emit. That was the example of a kind of black body, right? So I think now it is clear to you what we are moving towards, right? Now let's understand, if I talk about that, you have basically what kind of question they ask you. They will say that there is an iron block, right? This is a like example you will see in every single book. Iron you have, right? When you heat it, firstly it will go like reddish in color, then it will go white in color, then somewhere it will go blue in color, right? So this is what they are saying, that the color of the iron rod will start changing, right? So when we heat an iron rod, it first turns into red, then white, then it starts to be at blue color and at very, very high temperature. Now they're asking us why it is so, right? What is the reason that this iron rod, which is almost in black body, right? Not exactly, but almost. It is considered as a gray body, right? But we are taking that example only, right? Because in reality, we have gray bodies, right? So this iron rod, why it is changing the color, right? So it is changing the color. The reason behind it is, I'll show you this with the help of this simulation here, right? So this is the temperature, right? And you will have to see the peak here, okay? This is the peak. Can you see? This is the peak, peak. Can you see this peak here? This is the peak that you are going to focus on, okay? I'll change the temperature. You will have to see the peaks here. Can you see here the peak when the temperature is low, not that low, but still equal to a light bulb? Then the peak is here, right? When it has increased to the temperature of, let's say, 4000 Kelvin temperature, it is here. Now this peak is lying in the visible region, right? Now if you talk about this sun, now it is lying again, the peak is lying in the visible region. When you go again and again, it is beyond our scope, right? Now, first thing to observe here, whenever, this is from where they will ask the question, whenever temperature is increasing, can you see the maximum lambda, the peak that is maximum, that is moving towards the left side. That is moving towards the left side. Can I see that? Whenever I am increasing the lambda, this is moving towards left side. Okay? This is moving towards left side. That you are clear on? That means when lambda is, when temperature is increasing, lambda is decreasing, right? Because this is lambda, okay, wavelength, that is decreasing. Again, I'll show you. I'll increase the temperature, but maximum lambda will decrease. That means temperature and maximum lambda are inversely proportional to each other, and this is called Wien's displacement law. Okay, what this is called? This is called as Wien's displacement law. Let me just show you that. This is called as Wien's displacement law, and based on this, very interesting questions they can ask you, right? So what you can say, lambda max is inversely proportional to the temperature, right? For example, they give you this particular diagram. So now I'll tell you how they will ask you questions in the exam, right? Simple question will be asked here. They will say this is the graph and they will hide this thing, okay? They will hide this thing. Now they will ask you, you have to tell whether temperature T1 is greater than T2, it is less than T2, it is equal to T2, or you can't determine that, right? So we know that lambda maximum is here. This is lambda max. This is lambda max for temperature T1. This is lambda max for temperature T2, right? Temperature T2. So we can say lambda max of 1 is greater than lambda max of 2. Can we say that lambda max of 1 is greater than lambda max of 2? From this, can I say that if lambda max of 1 is greater than lambda max of 2, that means temperature of 1 will be less than temperature of 2 as lambda max is inversely proportional to the temperature. Students, tell me if that is clear or not, right? This is where they will ask you the question, okay? So it's a very, very detailed topic, but that much detail is not in your syllabus. So that's why I'm sticking to this thing only. If I go beyond this, right, you will get confused, right? But this particular question is very, very, very important for you, right? This is the law, and this is how they can ask you the questions based on this graph, right? Okay, now let's understand one more thing here. Let's understand one more thing here. That is, let me just show you that. Yes. So let's understand one more thing here. If you see, I'll just stick to any one random peak. Okay, this is the peak that I'm sticking to. Now we know that to at a constant temperature, if I'm fixing the temperature, it is going like this. Some radiations are falling in this region, some radiations are falling in this region which are not visible to us. Maximum radiations are falling in the visible region, right? This is the same case of light bulb, okay? Tube light, anything, like I'm taking as a random example, okay? So let's talk about this tube light. When you're sitting in a room, there must be some source of light, right? Just look at that source of light, right? You can see only some part of visible radiation out of that source that lies in this region. There are so many other radiation that it is giving you this. That's why there are heat radiations also that this light bulb or light is giving you that your eyes are not able to see. That's why this tube lights, bulbs, they heat our room. But now I am talking about tungsten bulb. I am not talking about LED bulbs. I am talking about tungsten bulbs, right? If you are sitting in that, right? So they give you heat radiation also that you can't see because most of the radiation you will see are not lying. This I am talking about temperature that is 5000 Kelvin. If I decrease the temperature, can you see this? Can you see this? The peak is so small. That means maximum radiation. If I talk about a light bulb, can you see for a light bulb, maximum radiations are lying not in the visible region. That's why maximum radiations your eyes are not able to see, right? That is the reason you can only see the things that are there in the visible region. That's why you can only see the glow from the bulb, but the glow, can you touch the bulb? No, because it's very heated up. That is heated up because these radiations that are lying in the infrared or any other region, right, that they are in, right? Other regions of electromagnetic radiations. Okay, yes, everybody? Okay, yes. So guys, that's it for black body radiations, right? Maximum that I can tell you, I have told you already. Wait a minute, right? Because more than this is not in your syllabus, right? Now, let's talk about other things here, right? This we have already discussed that lambda and T are inversely proportional to each other. Now, let's talk about Mr. Planck, right? You must have seen this H, right? Ma'am, 6.6 into 10 raised power minus 34 is the number, right? How many times you have used it? So this is the guy responsible for this particular constant, Planck's constant. Now, let's see why this person is so important to us. Why this person is so important to us, that lies over here, right? That lies here. I'll just show you. So what exactly happened here? This was the graph, right? This was the graph between, this was lambda, right? And this is your intensity, right? Intensity. This was the graph, okay? Now, scientists were doing some experiments. They were like, okay, so it's okay. We are getting this kind of graph. The graph is something like this, okay? This kind of graph they were getting, right? That it is decreasing, or to be more precise, it was something like this, right? Something like this kind of graph was there, I'm still not able to draw it that precisely, right? So wait a minute. Okay, this kind of graph was there, right? Now, scientists were actually getting confused here, right? Because the real, if you talk about, this is the real graph, okay? This is the real graph that they were observing from the experiments, right? That I have just showed you in the black body radiation. But you know what was the big question here? That if they assume, now how they assume, what is that? It is a too much detail, right? I will not get into it because you will automatically get confused. That is not in your syllabus, right? I'm just telling you how, see, we usually say this is black body radiation, this is Planck's quantum theory. But how this shift is happening from black body to Planck quantum theory, what is the reason behind that? That Planck has to come and he has to say that, okay, this is Planck's quantum theory. What was the reason behind that? Because the imaginary graph should be like this. This is the imaginary graph. This is the imaginary, or you can say not even imaginary, you should say expected graph. So, scientists were saying that if you are assuming that these electromagnetic radiations, these electrons, these particles, right, they are waves, then they should have this particular kind of graph, right? But according to black body radiation, you were getting this kind of graph, right? So many experiments were done. Now, no one was able to explain it, but then Planck explained this with the help of his quantum theory. He said that this electromagnetic radiation is not a wave, it's actually a particle. So everyone was like, how can you prove that? So he gave an equation which is not in your syllabus. So congratulations for that. That is not in your syllabus. So he gave some equation. He was like, okay, this is the equation. This equation, he put down all the values that he had from these experiments and he was able to explain the reality of this graph. So everyone was like, okay, science demands proof. If he was able to explain that why black body radiation is having this kind of graph, not this kind of graph, that's why Planck's quantum theory was true. Now it was a proof that yes, that means this theory is true. That means because transition, how Planck explained that this is not wave, this is particle. That was a big thing, right? And that's how he explained that, right? That is not in your syllabus. What is in your syllabus is what is Planck's quantum theory. So he simplified his equation. He said that E is equals to h mu. Now he said that if you talk about stairs, okay, he didn't say stairs, right? I'm just telling you an example here. This is stair and this is a ramp. This is stair, this is a ramp, right? Okay. On ramp, you are not counting. This is first, this is second, this is third. It is a continuous platform. But on stair, you are counting. This is first, this is second, this is third, this is fourth, this is fifth, right? And here, it is a continuous thing. It is a continuous thing. Now, what Planck said is, Planck said that these are not waves. These are actually existing in particles. They are actually existing in packets, right? Like you have stairs, first stair, second stair, third stair, all are equal. In the same way, you have packets of energy. Energy is not at all continuous. It is in the form of packets. And one packet will be equals to h mu. He said that one packet will be equals to h mu, where h is Planck's constant, that is 6.6 into 10 raised to power minus 34, right? And he made the term and he called the term quantum. Now we are not at quantum theory. We are just moving towards Bohr. After that, we'll talk about quantum. Right now, we are just telling that he said that one quanta is one packet. Okay, the one energy packet is called as quanta, and that is regarded as h mu. And if you specially say that what is the quanta of light? If you talk about packet of light, especially I'm saying that I'm talking about light. then that is called as photon. From there, whenever we click photo, we say photograph, right? That comes from photon, right? Photon means light. Light means that we are having one quanta, one packet, right? That is equals to h mu, where mu is the frequency. That's how we have Planck's quantum theory. The energy is emitted or absorbed not continuously but discontinuously in the form of discrete packets. Now Rutherford, can you see Rutherford was saying that electron is moving around the nucleus. Now this Planck's quantum theory is giving Bohr an idea that there can be discrete orbits. Can you see that? Can you understand that how science is interrelated to each other? How this Planck's quantum theory is going to give us an answer why Rutherford model failed and why we will have new model that we will discuss in the next class. Now I understand discrete orbits will be there because he is saying discrete packets, right? Okay, guys, right? So I think that's it for Planck's quantum theory. Now what is Planck's quantum? E is equals to h mu. So E is equals to h mu. Now tell me, C is equals to mu lambda. So mu is equals to C by lambda. So it will be hc by lambda. Okay, it will be hc by lambda. There are some shortcuts also for this thing that you need to, just remember the value of hc, right? That also I'll tell you, don't worry, right? Okay. Now, if you talk about that there are n number of packets, n number of photons, then it will be called as nh mu. It is number of quanta. It is number of quanta, and h mu is the energy of each quanta. Energy of each quanta. Okay, understood? Now, this is a very important conversion from 1 electron volt to joules. That is one. When you have to convert something to electron volt to joules, just multiply it by 1.6 into 10 raised to the minus 19, and that will be converted to joules. And these conversions, I have also talked about these conversions in my unit conversion lecture. You can go and watch that. That will really, really help you. Okay. Now let's do this questions of NEET 2021. Very simple question. Let's do this here, guys. Let's do this. It says that the particular station of All India Radio, New Delhi broadcast on a frequency of this. This is essay they have given you. Just focus on the frequency, okay? Frequency is given to be this much kilohertz, right? The wavelength of the electromagnetic radiation emitted by the transmitter will be what? Simple. C is equals to mu lambda. So, lambda will be equals to C by mu. C is already given to you. Mu, you already know that is given in kilohertz. Convert it to hertz and put the value of C here and you will get your answer. Was it even 1% difficult question? Tell me one thing, right? Was there something in this question that you really, really have to think upon, right? Put the value of C, put the value of frequency, and you will get your answer. There is no big deal in this particular question, right? And this was asked in NEET 2021. That's why we were saying that level has decreased. And now they will definitely increase a little bit, right? Now, NEET, this should be AIPMT, right? So, the value of Planck's constant is this, the speed of light is this. Which value is closed to wavelength of in nanometer? They are especially saying that in nanometer you have to tell of quantum with light. Okay. So, value of Planck's constant, we already know. We don't need your help. Speed of light also we know, right? Students, now if they ask you this question, they will not give you these hints, okay? Speed of light, Planck's constant, they will not give you this, right? So which one is the closest wavelength of quantum light with frequency? This simple, same thing you have to apply. C is equals to, there is no use of C is equals to mu lambda. There is no use of Planck's constant here because what you have is, they are asking you to find out the value of lambda, that is C by mu. and frequency you have here. So you just need to put down the value of C and mu. That's it. And you will get your answer, right? So Planck's constant is just given to confuse you that there will be some use of it. But in reality, there will be no use, right? Okay. Right, everybody? Okay. Yes. Now let's talk about the next question here. Next thing, that is photoelectric effect. Yes, everybody, let's discuss about photoelectric effect. Everyone ready for photoelectric effect or not? Right? Okay. So everyone, are you ready for photoelectric effect? Yes, everyone. Shall we talk about it? Now, if you talk about photoelectric effect, this is another effect that is focusing on particle nature of electromagnetic radiation. It's quite simple, okay? So let's take an example, right? I'll ask you this from your daily life, right? This is actually what is happening in our daily life, right? So I always give students this example because it is more relatable to you. So for example, you want to go out, right? So there's your friend's birthday party and you want to go out, right? Your parents are like, this is your NEET examination is coming and why you're going. Now you're calling your friend. You're like, my parents are like saying no. So what to do, right? I won't be able to come, right? So your friend is like, don't worry. I'll try. I'll try to, make them okay with you coming to my house, right? So your friend was like, okay. So I'm just give me one day. Tell me how your parents are, right? That what's their mood? Are they strict? Are they not strict? So according to that, I'll manage. Don't worry, I'll impress them, right? So like, okay, if you can, please do that. I want to go, right? So you're okay with that. Now, three situations are possible. Okay, three situations are possible here. This is Chintu, right? And tell me, beta, who is this? Who is this? This is Mintu, right? And this is their house. No, actually, Chintu should be in the house. Okay, this is the house. I am drawing that house that I used to draw when I was kid. Okay, so this is Chintu. This is Chintu is very sad at this point, right? He's very sad because Mintu, right? He's not able to go to Mintu's birthday party. Now, what will happen? Three cases are possible. First case is that, you know what I'll do here? This I did in last DNA batch, right? And students were like totally fan of this thing, right? So I'll make a table here, right? This is house of Chintu, right? This is Chintu's house. Okay, this is Chintu's house, right? And here you have Chintu. Chintu is in his house, he is very sad. And this is Mintu. And this is Mintu. Mintu is like questionable. He is like, I'm sad or happy, I don't know. Now, three cases are possible when Mintu will meet Chintu's parents, right? Three cases are possible when Mintu will meet Chintu's parents. And what are these three cases? First case is that Chintu's parents be like, Mintu is like, don't worry, it's just 1 hour and after 1 hour we'll also study. We'll also practice questions of previous year question of structure of atom, right? We'll also watch lecture of Diksha Ma'am, right? Don't worry, we'll study, right? It's just 1 hour, we'll have fun and after that we'll study. Now, Chintu's parents got so happy. They said, okay, fine. You go to party, right? Go to party and also gave him money. They're like, we are so happy that you have such good friends. Go and take this money also with you, right? Now, second possibility is that Chintu's parents are like, by these fake promises, you can't do anything, right? We know that what you're going to do. We know that you are not going to study, right? So, Chintu's parents are still like, okay, but you will be at home, so it's good. right? Okay, you can go, but we will not give you any money. So second option is go to party, but no money. Go to party, but no money. They're like, you have pocket money, take it, but we will not give you any money. Third case is, Chintu's parents are ultra pro next level strict. They are like, even if like anything is happening there is some seminar, there is any kind of physics questions you are going to solve, that doesn't matter to us. We want Chintu to be here in the house, right? If you're going to study here, right? We are not going to let him go with you. Now, what will happen here? Now they are sad. They are in the red zone. No party. No party. No going out. No going out. Right? So these are the three cases. Right? Now, just imagine this same scenario. Just imagine the same scenario. I'll tell you how. Just imagine the same scenario when you have metal here. This is the metal. Okay. This is the metal. Right. Metal is what? Everybody, what is metal? Metal is Chintu's house. Right. Metal is Chintu's house. His parents. Right. There is some incident light that is falling on it. And this incident light is Mintu. That is coming to his friend's house. Right. He is coming with frequency h mu, that I'll do this, I'll say this, and they will agree, right? Now, this particular metal, everyone's parent has some work function. Everyone's parent have some strictness level, right? That you do everything to, like, convince them, they will not be convinced, right? Some parents are okay, we are convinced, we are fine, right? So every parents will have their own strictness level. Similarly, every metal will have their own work function, right? Okay, now we can agree, but now we will not agree. But for a particular metal, that work function is fixed, right? For every single metal, the work function is fixed. That is called as h mu naught, right? Now what will happen? Three cases are possible. First is, if h mu is greater than h mu naught. If the convincing power of Mintu is greater than Chintu's parent strictness, then they will say, you go out, electron ejected with the kinetic energy. You also have money with the kinetic energy, right? Another case is if h mu is equals to h mu naught, that you are able to convince the parents to go out, but you can't take out money from them, right? So now what will happen? Electron will be ejected, but no money, right? No money, like go out, but no money, not even 1 rupee we will give you, right? Now this is the case where h mu is less than h mu naught. Now Chintu's parents are next ultra pro max level strict. They are like, you do anything, you beg here, we will not let him go, right? So here electron is not ejected. And guys, this is your photoelectric effect. That's it. This is your photoelectric effect. As simple as that. Okay? As simple as that. Okay, students? Now tell me if that is clear or not. Yes, students, tell me if that is clear or not. Right? Three cases will be there. In first case, electron will be ejected with kinetic energy. In second case, electron will be ejected. In third case, no electron will be ejected. These are the three cases here. Right? Okay. Now, let's talk about these things with the help of a simulation. Okay. We'll understand this thing with the help of a simulation also. Right? Let's see in practically what will happen. Here. Okay. I should have kept it here before only, but it's okay. Photoelectric effect. Okay. Yes. I think you must have understood this in physics as well, right? So I really hope so this works, right? because in photoelectric effect, it always gives some kind of, good, it's working, right? Okay, firstly, tell me if you're able to see this or not. Yes, guys, tell me if you're able to see this or not, right? Otherwise, I think I'll have to decrease the brightness, right? Okay, I think now it's fine. Otherwise, I'll start looking like a ghost. Okay, yes, it's fine now. Shall we experiment a little bit here, right? Okay, let's experiment. Now, let's try to change the intensity of the incident light. What is the intensity of the incident light, guys? Yes, okay. It's free. It's free. You can even see that. This is the website. You can see it's totally free of cost. Right? I had to just put it on Google and then whatever I feel is the best, I take it. Right? Okay. So now if you see this here, I am fixing the work function. What is work function? H mu naught is called work function. Right? The energy of the metal, right, that is called as work function, right? Okay, so I am fixing the metal to sodium. I have fixed the metal to sodium. I am fixing the intensity to 100%, right? I am fixing the intensity to 100%, right? Now I'll be changing the wavelength, okay? One by one I'll be changing the wavelength, okay? Right? Now we know that here lambda is maximum, mu is minimum. If you remember electromagnetic radiation spectrum, I told you here lambda is maximum, mu is minimum. So I'm increasing the mu, I'm increasing the energy of the incident light. Can you see? Can you see? Red, there is no electron that is being ejected. Okay, let's put it to yellow. Electron not being ejected. Green, one electron is being ejected at a very, very small speed. Electron is moving slowly, 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 slowly. Right? Now, can you see this here? Electron is being ejected. Can you see this here? Can you see the speed of the electron which are coming from this particular wavelength has increased, this frequency has increased. Let's make it to UV region. Can you see it has increased more? Let's increase it more. Now the speed has increased more. Can you see that? Can you see the fluctuation of when you are increasing the frequency, how the kinetic energy is increasing? These electrons are so fast. These were so slow. Now, again, if I decrease it here, can you again see it has again decreased? That means this frequency is relation with the kinetic energy, right? Can I say that more is the frequency, more will be the kinetic energy, right? Okay, more is the frequency. I have fixed everything else is fixed. I am not changing anything else, right? This is how these conclusions are made based on the experiments, right? This is how these conclusions are made based on the experiments, right? So now we can guarantee that yes, frequency and kinetic energy is related. Number is not increasing. If you see this very carefully, if I increase it to this level, number is not increasing. Number is same. It's just that speed is increasing, decreasing. So frequency and kinetic energy are related to each other. Keep this in your mind. This is a very important point, right? Okay. Now let's understand. I am fixing the frequency. Let's say I am fixing the frequency to this violet, right? Now I'll be changing the intensity. Okay. You see this. I'll be changing the intensity. Intensity is, let's say, very less here. Okay. Can you see? First, let me see the intensity as 0. Okay, one by one I'll increase. You will see number of electron ejected will increase. If I increase it, 1, 1, 2, very few electrons are being ejected. Speed will not change. If you see this, speed is still the same. Number of electrons are increasing. Speed is still the same. Speed is not changing. Number of electrons are changing. Can you see that? How intensity is proportional to the number of electrons ejected, right? So shall I write it here, guys? Shall I write it? These two conclusions, I'll just write it here. These two conclusions that we have drawn here. That first conclusion, let me see, I'll write it here. Observations we have already talked about, right? Observation I showed you there only. I'll talk about the conclusions, right? So first conclusion is that, or observation or conclusion, whatever you say, right? First is that frequency of incident light, incident light is that will change the kinetic energy of ejected electron. Kinetic energy of ejected electron. That will change here. Second part is, I am saying that you have intensity, right? You have intensity. Now, this intensity, how it is going to affect, right? This intensity means number of photons of incident light, Intensity means incident. Why I'm writing wrong? Incident light, okay? Now, intensity means number of photons are more. More the photons, more will be the intensity, right? Now, each photon is going to eject each one electron. That means one photon will eject one photoelectron. Electron that is ejected is called as photoelectron. So, more the intensity, more the number of photons of incident light, more will be the photoelectron ejected. Photoelectron ejected. Okay? That means one photon is going to eject one electron, right? Now, you know what is the main question here? That, ma'am, why one photon and one electron? Because if one photon, this is, let's say, photon, okay? So, I'll just, okay. So, let's say this is photon, right? This is the electron. This is electron, right? What will happen here? When this photon will strike here, it will collide here. This photon is going to collide here, right? It is going to transfer its energy. Wait a minute. It is going to, where should I draw? Okay. This photon will collide here and it is going to transfer its energy. While colliding, and that's how energy will be transferred and one photon will eject one photoelectron. Okay, right? Okay, everybody, clear, right? Shall I move ahead? Now understand few things here, that what is the relation here? As I told you, where should I write it? Because after that we are going to see the effects here. So I would write it here only, right? So, see, one thing is very simple, that H mu is equals to H mu naught plus incident light is equals to the work function of the metal, that is H mu naught, plus kinetic energy. Okay, it is also written as, this is written as energy of incident light, right? You can write it as EIN, right? This is written as work function of the metal, and this is written as kinetic energy, which is also written as half mv square, right? Now, if I talk about this kinetic energy in terms of this, the same thing that I have written here, and you know what is this called? I am just writing this here. This is called work function. And one more thing to remember here is that mu naught energy, mu naught is called the threshold. Threshold means minimum frequency required. Threshold frequency, and lambda naught is threshold wavelength. So this is the minimum frequency that is required to eject electron, right? Because we know that mu should be greater than mu naught, only then this is possible. So mu naught is the minimum frequency. Can you tell me, if I am saying this is the minimum frequency to eject the electron, will this be minimum wavelength or maximum wavelength? right? It is going to be opposite because energy is also opposite. Na? E is equals to hc by lambda. If this lambda that you have of incident is less than lambda naught, then this will be greater. Only then this is possible, right? So lambda naught is going to be the maximum wavelength here. That you should remember. Okay, right, everybody? Ma'am, when is the next session for class 12th NEET? That is on, I think, Tuesday, right? Guys, I have already taken, I think some of you have already missed, I have taken on Wednesday, that is yesterday, I have taken one lecture of electrochemistry where I have discussed conductance, conductivity, all these things I have already discussed there, right? So you can go watch that lecture at 2x speed, right? If you have already covered, then also you should watch it, right? Okay, because that was in the morning, so I think some of you don't know about it, right? Okay, so let us see this here, right? That is it, that we have done, right? This also we have done. Now let's talk about stopping potential. What is stopping potential? It is, I want to stop the electron from getting out. I'm like, no, I don't want you to get out, right? So I will apply external potential, that is called as stopping potential, and kinetic energy is equals to charge into stopping potential. And we know that here we are talking about electron ejection, so charge is nothing but that is electron. So it will be E into Vs, where Vs is the stopping potential. So you can say when you are putting the values here, this will be h mu is equals to h mu naught plus EVS, and that is going to be the formula, right? Where Vs is the stopping potential, right? Okay. Okay, now let's discuss some graphs here. Now, guys, let's discuss some graphs here, right? Okay. So, let me see what is the time, right? We still have time, okay? So, let's discuss the graphs here, right? So, graphs are very important in photoelectric effect, right? I'll show you some graphs with the help of simulations also, right? So, go through them in detail, right? Might be you will feel bored out of that, right? But focus on this because graph is where from the graph is the one thing from where they ask you the questions, okay? Right? Okay. Yes. Very good sign. Very good sign. Okay. So let's see that. Okay. So effect of frequency on the photoelectric effect. Okay. Each graph we will understand, right? So this is the first graph, right? Let's focus here. Ignore this graph for now, right? Let's focus here. Here what you have is energy, right? What is the incident energy? No, this is not the incident energy. Kinetic energy. This is kinetic energy versus frequency. So I'll just write kinetic energy here. This is kinetic energy versus frequency, right? Tell me one thing, right? If mu is less than mu naught, will there be any electron ejection? No. So when this is frequency, this whole thing is showing you frequency. When frequency is less than mu naught, there is no kinetic energy. Why? Because electron is not ejected. How you're even thinking about kinetic energy? So that means between these things, there is no electron ejection, no kinetic energy. Once you reach this particular point where you have mu is equals to mu naught, I'll just write it here also. In this point, what you have is mu is equals to mu naught. So at this point, when mu is equals to mu naught, we know that there will be electron ejection, but there will be zero kinetic energy. So that's why it is zero on kinetic energy. When mu is greater than, you can say mu is equals to mu naught, then kinetic energy is equals to zero. Okay, mu is equals to mu naught. When mu is greater than mu naught, then we know that kinetic energy will start increasing, right? As mu increases, there will be kinetic energy will be there, and we know that as mu increases, kinetic energy will start increasing. That I have told you in the observations part, right? So as mu is increasing, kinetic energy is also increasing. So that's why from here it is not a straight graph. From here it is a straight line graph. Okay. Now let's understand this thing, that is electric current versus light frequency, right? So tell me one thing, what I told you. What I told you. What do you mean by current? Current means, guys, what is current? How you will have current? Current is dependent on the number of electron ejected, right? Now tell me, when you are increasing the frequency, was there any effect on the number of electrons ejected? No. Intensity was affecting number of electron ejection. This frequency had no effect on the number of electrons. It's a simple observation that I told you here as well. I'm going to write it here so that every single time I don't have to write it again and again. So frequency is changing kinetic energy, and intensity or number of photons of incident light is changing the photoelectron. That means this is nothing but this is current. This is nothing but this is current, right? So can you see how it is changing? So that's why for one particular frequency, for one particular situation, right, for one particular intensity, current is going to be same no matter the frequency is changing. But remember, frequency should always be greater than mu naught. Only then this current is possible. Otherwise, electron ejection is not only possible, right? Okay, so these were the two graphs, right? Now complexity of the graph is going to increase, right? So more attention is needed here, right? So if you talk about electric current here, right? Electric current and light intensity. As I told you, as intensity will increase, number of electrons will increase. I have also already showed you there that how when you increase the current, when you increase the intensity of the incident light, right? How this number of photons were increasing. So I'll just show you here as well, right? If you see this, intensity is 0, right? No photon, no photoelectron. So it is, I'm increasing. Can you see? Number of photoelectrons are increasing. Speed is same. Number of photoelectrons are increasing. Right? Okay. Now, let's understand this thing. Right? That is also done. Now, next is stopping potential and frequency. Now, when you will stop someone, when they are going out of the house, right? They are sitting in the house, we are still saying, you can't go out, you can't go out, you can't go out. They'll be like, I'm sitting in the house only, right? So when someone is going out, that means only then you will stop them, right? So stopping potential will be applied only when electron is ejected. So that's why when frequency is less than mu naught, there is no stopping potential, right? There is no stopping potential. Stopping potential is 0, right? This is over plottation of the graph. You can ignore this for now, okay? You can ignore this for now, right? For now, you can ignore this. This is over plot of the graph, right? So if you see this, for mu less than mu naught, there is no stopping potential because there is no electron which is ejected. But once the electron is ejected, we know that more the frequency. What is there? Why it is a straight line? More the frequency, more will be the kinetic energy, right? And if you remember, I told you kinetic energy is equals to EVS. Kinetic energy is directly proportional to Vs. So more kinetic energy means more will be the stopping potential, right? Students, can we also say this, that if speed is very fast, electron has very fast speed, so it will take more potential to stop that electron, right? So that's why it is directly proportional here, right? Okay, understood, right, everybody? Now, and if you're really liking this lecture and you still don't comment in the comment section, you still don't like the video, right? So much I am doing for you guys. Still I have class in JEE, I have class at 8 p.m. Still I am standing here, right? I am teaching you everything in detail. Why? Because I care for you, right? So you should also care for me. It's like give and take, right? It's caring for each other, right? Okay, so let's talk about this particular last two graphs. You might find difficult, these two graphs. Okay, these two graphs you might find difficult, so let's talk about them, right? So here what you have is photoelectric current, right? This is the photoelectric current, this is anode, this is retarding potential. See, this is an experimental thing, so I'll try to explain you as much as possible. So what happens if you talk about the potential that you apply, right? That potential, how it is going to change, right? Let's talk about this. This is actually the frequency, right? Okay, this is actually the frequency. Here they are talking about mu1, this is mu2, this is mu3, and how photoelectric current is going to change. That means how number of photons are going to change, right? So they are saying that if you're stopping someone, right, then see, we know that when external potential, we are trying to, like, we are making a potential that is going to stop these electrons to get out of this. What will happen there? Current will go down. That means number of photons will go down. What is that? See, we know that simple thing is that we know that when we apply the stopping potential, right, what will change? Number of photons will ejected will be less. That means the current will be less. This is the same thing that is happening here, that when you apply the retarding potential, the stopping potential, in that case, the current is going to decrease because the electron ejected will be less. But when you're not applying any stopping potential, then definitely what will happen? The current will increase, increase, increase. But there will be a point when it will not affect, right? Where current will become constant, because current will also have its saturation point. More than that, the current will not be able to increase, right? Okay, so this is, you can understand this with the help of this particular example that I gave you. You can also see this experimentally as well. Second is, I'll show you both of them, right? This is again retarding and simple potential. How photoelectric current is changing, but here we are taking three kind of intensities here, right? I1, I2 and I3, right? So let's talk about this thing, right? This is I1, this is I2, this is I3, how it is going to change. Same thing. We know that as you apply the retarding potential, right, what will happen? Number of photons will decrease. That's why the current is going to decrease, right? But now you will see also one thing, that what will happen when you don't apply the stopping potential, right? The current will definitely increase, but at one point it will become constant, that will become saturated current. Okay, understood? Very rare chances that they will give you these two graphs, but still if they give you, you should know that how to do this. Okay, yes everybody. Let's talk about this particular question. When the electromagnetic radiation of wavelength of 300 nanometer falls on the surface of metal, that means this is particular is lambda, surface of the metal, electrons are emitted with the kinetic energy of this. Okay, what is the minimum energy to remove the electron of the metal? That is work function they are asking you. So we know that hc by lambda, that is h mu, is equals to work function plus kinetic energy. So work function is equals to hc by lambda minus kinetic energy. So h is nothing but 6.6 into 10 raised to power minus 34. You multiply it with 3 into 10 raised to power 8, right? Then you have lambda, that is given to be 300 nanometer, right? And here it is nothing but it is minus of kinetic energy. Kinetic energy is 1.68 into 10 raised to power 5 joule per mole. Okay, so all the values you will put here and you will get your answer here, right? Okay, all the values you put and you will get your answer. Wait a minute, there's some wait a minute, the accumulation of this falls on surface of metal, electrons are emitted with kinetic energy this. Okay, the minimum energy needed to remove an electron. Okay. So here the catch is that they have given you 1 mole and an electron, right? So two things are there. They're asking you for 1 electron and they have given you energy for 1 mole, right? Okay. So if you talk about energy for this, you can ignore. Kinetic energy is given for 1 mole, right? If you talk about energy, that is hc by lambda, right? That is you are calculating for 1 electron. If you calculate it for 1 mole of electron, that will be this much, right? You just need to multiply it with Avogadro's number, right? So this is for 1 mole, that is the energy of incident light, and this is the kinetic energy, that is also for 1 mole. When you subtract it, you will have this answer, that is for 1 mole, that is a work function for 1 mole, right? Okay. And here what they have asked you, minimum energy needed to remove an electron from the metal, right? So they are asking you to remove 1 electron from the metal, and this is the energy, okay, right? So the work function that you have here is nothing but h mu naught, that is defined as the energy required, the work function for 1 mole, right? Okay. Next is the energy of 1 mole of photons of radiation of wavelength this. Isn't it the same one? Isn't it the same thing? Energy of 1 mole of photons of radiation of wavelength. This is simple. This is E is equals to hc by lambda and multiplied by Avogadro's number. You will get your answer, right? And now this is important for you, that I told you that usually you have E is equals to hc by lambda, but you can just remember it as 1240 lambda in case of nanometer, right? This is actually a formula only, that is a direct formula, so that you don't have to do that many calculations in the exam, okay? So to avoid the calculations, we have this particular formula. Now, if you see, when you put this value, I'm just giving you direct how to solve, right? Try to do the calculations yourself, right? Okay. So energy of 1 mole of photon means you have to multiply it by Avogadro's number. Wavelength is given to you. First, you will calculate energy of 1 atom, that will be this much electron volt. And here remember that when you put this formula, energy is in electron volt, not in joules, right? Okay. So this is energy in electron volt. For 1 mole, you will multiply it by Avogadro's number and you will get your answer. Whatsoever is asked to you in the exam, if they are asking you kilojoule, convert it into joules and then kilojoules. How to convert it into joules is multiply this by 1.6 into 10 raised to power minus 19. In today's lecture only, I showed you the conversion of 1 electron volt to joule, that is 1.6 into 10 raised to power minus 19, right? Then convert it into kilojoule, right? Per mole is already there because we are talking about 1 mole, right? Okay. Understood, everybody? Then there is this statement based question. In a photoelectric effect, the electrons are ejected from the metal surface as soon as beam of light of frequency greater than threshold frequency strikes on it, right? That is true. If h mu is greater than h mu naught, it will definitely be electron ejected from the metal. It will be ejected, right? Okay. When the photon of any energy strike on an electron atom, transfer of energy from photon to electron take place, right? That is absolutely true, right? That the transfer will take place, right? That is also true, right? Now, if you see this question here, right? In this question, you need to answer why. See, assertion and reasoning both are correct, but is it the explanation or not, that you have to see, right? So, why electrons are ejected from metal surface as soon as frequency greater than threshold frequency strikes? Because photon of any energy strikes on electron, transfer energy from the photon to electron. That's why electron ejection takes place, because photon is giving its energy to electron. That's why electron is being ejected. So that means that is the correct explanation also. So answer will be A. By mistake, here it is marked wrong. So answer will be A, right? Okay. Now, this is the additional topic that I am teaching you, the last topic of the class, that is atomic spectra. Okay. that is atomic spectra. Let's discuss about atomic spectra, because in the next class we are going to discuss about Bohr atomic model, right? So you need to have some information about spectra, and it's a very, very small topic. As such, they don't ask you questions from these spectras, but to understand what we are going to do in the next class, you need to know this particular thing, right? So if you talk about atomic spectra, that is nothing but spectra in a group or band of wavelength, right? So basically spectra is the band of wavelength or colors. And the study of emission and absorption spectra is called spectroscopy. So it's actually a very nice study. Spectroscopy, one of my favorite subjects in MSc and BSc. So it's very interesting, NMR spectroscopy, when you do, like, organic compounds. Now you just see the organic compounds, but when you see the peaks of the organic compounds, how they looks like. This is how they look like, right? This is how they look like. So for example, something has this kind of spectra, right? This kind of spectra. And when you study these peaks, that is called the spectroscopy. When you study that this peak is here, it has 3 peaks here, it has one doublet here, one triplet here. This is what we call the study of the peak, study of spectra, that is called spectroscopy. Very famous one is NMR spectroscopy, not at all your scope, right? Your scope means not at all in your class, right? In class 11, 12, it is not there, right? So why I told you this, so that you can have that imagination that what exactly this is all about, right? So spectrum is a group or band of wavelengths. What are these? These are the bands of wavelengths that you have, right? And the study of emission and absorption spectra, right? But for that, you need to know what is this emission and absorption spectra. And this is all what you have in your syllabus, definition of emission and absorption spectra, that's it, right? So let's talk about emission spectra. Spectra of radiation emitted by substance that has absorbed energy is called an emission spectra, right? Okay, so spectrum of radiation of emitted by a substance that has absorbed energy, when the radiation emitted from a source are incident on a prism. I'll just show you the diagram. This is the diagram basically. So you have a white light that is passing through the slit, right, to have some parallel rays. This is falling on the prism, and from that you see a spectra, right? So this particular spectra that is emitted because this particular prism has absorbed some light. That's why it is emitting different all the colors of white light. That is called as emission spectra, right? Okay, when something has absorbed something, some prism, now here prism we are showing, so prism has absorbed something. After absorption, it is emitting those lines, right, in a continuous form. Now two kind of spectras will be there. Here you have continuous spectrum, all the colors are there, Vib-Gyur, all colors are there, right? That is a continuous spectrum, right? And that is obtained on a photographic plate, right? Now let's see what is a discontinuous spectra, right? So in a discontinuous spectra, for example, what you have is, this is raised, let's say they are saying that excited hydrogen sample, right? Electrons are excited. See why I'm showing you all of this, because this we are going to study. I'm again going to talk about this, right, in the next lecture, right? So see this. This excited hydrogen spectra, this will fall into the slit. This will pass through the prism. But it is in such a way, because the white light, we know that, see, one thing is, we know that white light will have all the colors, right? That's why white light is emitting all the colors, Vib-Gyur, right? See, if you have knowledge of physics, chemistry and bio, so that you will emit everything. First you will absorb the knowledge, then you will emit the knowledge in the exam, because you have knowledge of all the three things, right? If someone has only good knowledge about bio or chemistry, right, physics, so I don't expect, right? So if you have knowledge of only one or two things, right, now you will only emit what you have absorbed, right? So here, this excited hydrogen spectrum does not have all the wavelengths. It has some specific wavelengths. So it is going to emit only those wavelengths that it has. Okay, you are going to do questions of only those topics that you are good in, right? So here it will emit some specific spectra, and that is called as emission spectra, and this is useful in the fingerprint of a element. See, basically every single element like hydrogen will have a different spectra, right? Other helium, other gases, oxygen, nitrogen, they will all will have different spectra. They all will excite the electron to a different level, right? That's why excited electron will have a different wavelength. I know all of this is going out of your head right now. We will talk about this in Bohr model, that how electrons are excited, right? Okay. Right now, just remember that every single atom will have different spectrums, right? Okay. Now, let's talk about absorption spectra. This is all emission spectra. Again, one photo of this. Excited sample of any gas, it will pass through the prism. It will give you some specific wavelength, right? So it is absorbing something, it is emitting it. That is emission spectra, right? Other spots will be dark where it is not emitting anything, right? Now, what is atomic spectrum, right? That is same atomic emission when from the atom it is coming out. The light emitted by sample of excited hydrogen atom can be passed through prism. This emission spectra, which is photographic recording of separated wavelength, is called line spectra. Why? Because here these lines are being shown here, right? And this is what nobody was able to explain. Hydrogen spectrum is what is our next topic that Bohr is going to explain, right? Bohr is going to tell why it has this kind of spectra, why only some specific lines it is giving. Any sample of reasonable size contains enormous number of atoms. This we'll talk about in the next lecture because that is important, but after Bohr model, right? Now let's understand absorption spectra. Absorption spectra is you have some absorbing sample. This is white light, okay? Now white light, this is white light. Here I have some absorbing sample, right? That is absorbing some wavelengths, right? Okay, so it's the same situation when you are going into the exam hall, right? And your friend is like, tell me, which question is important? This one is important. Okay, this one is important. This one is important. Okay, this one is important. This is H is equals to H mu is equals to H mu is equals to H mu. This is how your friends behave. I know even I have done that, guys. Even I have done that, right? So outside the exam hall, we all do this, right? So this is what we are doing. Someone knows something, we are trying to absorb it, right? And we don't. And in this case, sometimes what people do, they're like, no, E is not is equals to H mu. You are wrong. Now the person who have already studied, he will get confused that, okay, that means my 5 months of study is a waste. I don't know that E is equals to H mu or not, right? So that is the thing. So here some white light is coming, which has every single wavelength, every single wavelength. Some absorbing sample is there. It is going to absorb some wavelengths. Then this white light, after absorption of some wavelength, it is going to pass through this. Then it will give you a spectrum which has some parts missing. And these parts that are missing, these lines that are missing, are because of these absorbing sample. Okay? Are because of this absorbing sample. Beta, tell me if that is clear. Emission is directly you have a white light or you have any hydrogen or any gas excited electron, pass it through the prism. What is the light that it has absorbed? It will emit that light. That is emission spectrum, right? Atomic spectrum is when we use any gas and we make the emission spectrum of that. Absorption spectrum is that we are making some absorption sample in between, which is eating the extra wavelengths. And it's like you have whole pizza, right? And now your friend is cheating, right? Your friend is like side by side, he is eating 3-4 slices and you are left with only 3 slices. So we are able to only see 3 slices because some slices your friend has already eaten, right? that is absorption spectrum. Okay, right, everybody? Right. So atomic absorption spectra is when white light is passed through an unexcited atomic hydrogen and then through a slit-end sample. That means we pass this through a unexcited atomic hydrogen, right? This particular absorption sample is nothing but this is the hydrogen, right? So whenever, see, atomic means whenever you put atom into it, that becomes atomic spectra, as simple as that. Okay, right? So in that case, the spectrum that you will observe will be your absorption spectrum. Okay, guys, clear, right? I have to speak for 2 more hours. I don't know how I'm going to do that, but I'll do that, right? So, guys, that's it, right? Clear, everybody? Let me know in the chat box. If you're done with your chit-chatting, then tell me in the chat box if that is clear or not. How was today's lecture? If you feel that, yes, I have put enough energy, right, for you guys to make you understand these difficult topics, then do write it in the comment section, because even I feel happy, guys. Even I have heart, right? Even I have emotions, right? Even I feel happy that you guys are appreciating the efforts, right? And guys, this is our homework. This is the question number 1, right? And this is question number 2, right? You can take the screenshot of question number 2 here. This is the question number 1. Take the screenshot here, right? Okay. And do the homework, right? I'll wait for this. This is our Vedantu NEET English channel, right? And I am waiting for you guys to answer all the questions in the comment section. And nothing big deal. How do you comment, right? Over here, you will see that the comment section is there. All you have to do is comment over there your whatever you feel about the class, right? Or your sometimes after 2 hours of speaking, your brain stops working, right? So whatever you feel about the class and the homework, right? Okay, I just got zoned out. So guys, now if you see this here, right, this is our DNA NEET 2026 batch. This is especially for the 12th class students and droppers, right? Ma'am, are you guys teaching in that batch? Yes, we are there in the batch, right, along with the other teachers, right? And even today, we were doing a solution chapter in the batch, right? And it was very interesting. You can ask from the students itself how they're enjoying the batch. They're totally loving the batch. Reason being, there are quizzes in the batch, there are leaderboards in the batch. After now, this 27th of July, students have their mock test, right? So whatever we have done, and it's not the first mock test, already 3, 4 mock, 2, I think 2, 3 mock tests already we have done, right? So similarly, after every 15 days, mock tests are going on, right? And guys, we are also providing the Tattva solution, the Tattva modules we are providing, and we also give you the questions that you need to do from the Tattva module. So all these things are there at just 4,999. You can view course plans and you can see this over here. If you want, along with all the things that I just told you, that if you want All India Test Series hard copy and NEET quick revision cards, that are these cards, right? That is for your quick revision. Then guys, that particular course is at 7,999. So everything will be delivered at your home, right? Now, what about these cards? See, in these cards, actually everything is written in a very short format. So then you don't have to make your own short notes. That already we have done. And that were very colorful and pocket-friendly notes that you would want to revise, right? That will make you revise, right? And then if you want Tattva 11th and 12th NEET books, right? NEET modules, that will be delivered at your home, right, in the hard copy version at 10,999. Modules will be provided in these 2 cases as well, but here it will be soft copy, but here it will be hard copy. So based on what you want, you can select the DNA batch that you want to get into, right? Okay. So guys, that's it for today. And I'll wait for your comments in the comment section. And till then, bye-bye. Take care. See you all in the next class. Bye-bye.